Differential calculus is very powerful. And as with any language, it derives its power from the idea behind it, the derivative. The derivative is to kinematics what the wheel is to travel. A simple yet very effective means for getting from one place to another. And to get just the right perspective of what else a derivative is, nothing works better than a little exercise. To begin with, a derivative doesn't apply only to a body in horizontal motion, nor for that matter, only to a body in vertical motion. Up, down, any which way, a derivative is the rate of change of any function at any exact point or instant. As illustrated by Galileo's law of falling bodies, speed is the derivative of distance. But it's more than that. A derivative can represent the rate of change of anything. For example, the population density of dolphins in relation to increasing or decreasing water temperature, or the rate of change in the volume of a balloon versus its surface area, or even the rate of change in the price of a pizza with respect to its size. Clearly then, the concept of the derivative goes far and wide. But the mechanical process of the derivative, differential calculus, needs a practical approach, or the concept goes nowhere fast. Eventually, without the rules of differentiation, the simple concept of the derivative becomes an uphill struggle. In the long run, it helps to pick up a few more definitions along the way. So before it's too late to turn back, consider the factor of steepness. On the incline, the steepness is the ratio of the change in elevation to the change in horizontal distance. This ratio, a number, is called the slope. For example, suppose the elevation of an incline increases 15 meters every 100 meters. The rider moves upward 15, horizontally 100. The slope is 0.15. A hill with a slope of 0.3 is twice as steep as one with a slope of 0.15. The bigger the slope, the steeper the hill. When the slope is large, it's no small feat to get to the top. When the slope is next to nothing, near zero, it's easy going. And when the slope is negative, it's downhill all the way. Although mathematics can be easy going, it does have its peaks and valleys. And it always has. Nobody knows who first asked the best way to get from here to there. But the answer, in algebraic terms, was first offered by a French mathematician named Fermat. In 1629, he came up with the idea of finding the tangent line to an arbitrary point on a curve. In 1638, Fermat shared his discovery with his countryman, René Descartes, who had his own method for finding tangents to algebraic curves. Many of these mathematical ideas, especially those of Fermat, were further developed by Wilhelm Leibniz and Isaac Newton into a general and systematic method of mathematical analysis, differential calculus. Setting history aside, at least for the present, some timely questions remain. For example, on a smoothly changing curve, there's a constantly changing slope. How then, in today's language, is a slope calculated at any given point? To determine the slope at a particular point, here for example, Simply take another point on the hill. It doesn't matter where. Now connect the 2 points with a straight line. That line is called a chord, and its slope depends on the location of the second point. If the first and second points are reasonably close, the chord is a reasonably good approximation of the bike's path. Now, move the second point closer to the first. Move it even closer. The slope is a number, and as the points get closer together, the number gets closer to a certain value. It's reasonable to call that number the slope of the hill at that point. The line with that slope through the point is called the tangent line. And the tangent line is just what the chord turns into as the points get closer together. And the slope of the tangent line at that point is the slope of the hill.